All right, so welcome back. This is a different video from the series of Calculus 2 preparation videos that I've been making. So in particular, today's video, I really want to focus on a concept that is taught in Calculus 1, but sometimes students would have a lot of trouble um, having to show the definition of the limit. So we're familiar with the intuitive definition of the limit, which is given by this notation here. So the limit as x approaches a of f of x is going to be L. So we often wish to prove that the limit is true using the definition of the limit, which, as I mentioned, is not very easy for some students who have just learned it the first time. But as you get the practice of using the definition of the limit, you'll most likely get a lot better at doing them. And it would should almost be an instant of what the step that you would have to do. So let's have a look at the first definition. So the first definition here, we said that, well, if we had the limit as x approaches a of f of x is L, so that's going to be the standard limit, then we say that for every epsilon greater than 0, there is some delta greater than 0 such that if the distance between x minus a is less than delta, then the distance between f of x minus L also has to be less than epsilon. So if you want to visualize this, so say we have a function that goes maybe somewhat like this, and we want to show that, well, if this point is the limit, so this is going to be a, and that means this definition or this limit here is going to be the L. So if we consider two bars here, so these are going to be the delta lines. So if we make delta to be arbitrarily small enough, so here is a minus delta, and here's a plus delta. And same thing with the limit lines as well. For on the y-axis, if we draw a line that goes above here, and if we say, well, this is going to be L plus epsilon, L minus epsilon. So over here, as we make delta arbitrarily smaller, so as we get closer and closer to A, then that means the value of the L plus epsilon should be getting closer to the limit here, that is over here. So as we get closer to the limit here, these lines should also get closer to this point over here. So that means if we make delta to be arbitrarily small and epsilon to be arbitrarily small, we should get that, well, the distance between the function, so the function is this line, and the limit should be less than epsilon. So that's the goal that we're trying to show here. So majority of the time we want to find this region, work with this region here. All right, so let's have a look at some examples here. So we want to, first of all, prove that the limit as x approaches 2 of x is equal to 0, or 2. So visually, if I create a sketch of the linear function, okay, so this is the linear function. So we have the limit at 2. So let's say this point over here is 2. And we want to show that this point, so this limit over here is also 2. Okay, so that's the limit on the y-axis, and the where it's approaching is just going to be 2. So what I want to show is that if we choose a delta to make it arbitrarily, if we find a delta such that we have 2 minus delta, 2 plus delta on this side, and if we choose, or if we have any epsilon greater than 0, that this side, so this is going to be 2 plus epsilon, 2 minus epsilon. So our goal is to show that the distance between the function and the limit is going to be smaller than epsilon here. Okay, so that's the goal here. So let's start with the definition of the limit here. Well, we know that, well, if we have x minus 2 less than delta, we have f of x minus L is less than epsilon. So our f of x is going to be the x, the L is going to be 2, and the A is going to be 2 as well. So first of all, the way we're going to start this is say that, well, let's say we have epsilon be an arbitrary value. Because we're saying that if we allow any epsilon that is greater than 0, then we could just let it be an arbitrary value. So if then we say, if the limit as x approaches 2 of x is equal to 2, then there has to be a delta greater than 0, such that if x minus 2 is less than delta, then we want to show that the function f of x minus L is less than epsilon. So then we have that f of x minus L, which is equal to x minus 2. Okay. But here, we already know that, well, we have this value here, x minus 2, in absolute values. We also know that, by our assumption, that the absolute value of x minus 2 is less than delta. Right? So that's the first step. So this part here, we need to choose a delta such that in the end, we could get epsilon by itself at the end. So we want to show that this inequality, x minus 2, is less than epsilon. So the goal here, so show that x minus 2 is less than epsilon. So what delta, we have to choose a delta to make this happen. And the choice of delta in this case would just be a very simple one, because if we just set delta to be equal to epsilon, then we just simply have that, well, x minus 2, which is less than delta, but is equal to epsilon. So because we have that the x minus 2 is less than epsilon, then this implies that, so that means the limit as x approaches 2 of x is equal to 2. And the proof is done. So that's the general step here. So let me go through this. So the first thing that we said was if we let epsilon be arbitrary, so that's going to be the first step that you want to do. The second step is know what you're given. So since the limit as x approaches 2 of x is 2, then there has to be some delta greater than 0, such that if this distance is less than delta, then the function also has to be less than epsilon here. The function minus the limit has to be less than epsilon. So, and then this part, we just had to do some algebra here. And then we have to go to a stage where we can choose a delta so that we can make the function minus the limit less than epsilon, which leads us to this part here. Okay, so this one wasn't really that really complicated. So this was the second step, this was the third step, and this is the fourth step. So usually it comes in 4 steps. All right, so let's have a look at the second example here. All right, so the second part here is that we want to prove that the limit as x approaches 2 of x squared is equal to 4. So let's have a visual. So visually, it would look something like this. So if we have the parabola, let's say that here is 2, and this is 4. So this is 2, and this part is 4. So once again, we want to show that, well, if we have delta to be small enough, or epsilon to be small enough, and we choose a delta that can also make it smaller. So the delta here actually has to be the function that is in terms of epsilon that we choose. So that's 2 minus delta, 2 plus delta here. And then we have 4 plus epsilon and 4 minus epsilon here. So we want to show that it's going to be within this region here. All right. So same thing here. So we're going to say, well, let epsilon be arbitrary. And since the x squared, or the limit as x approaches 2 of x squared is equal to 4, then there exists a delta, which is the delta that we had to find, such that if the distance between x minus 2 is less than delta, then that means, well, the function f of x minus L, which is equal to x squared minus 4. Okay, so notice that this is simply a difference of squares here. So let's go ahead and factor that. So we have x minus 2 and x plus 2. All right. So here's the thing that we have here. We have that, well, we have the x minus 2 is less than delta. So we could change this part and make it less than. So this part is going to be less than. So we have a delta here. And then we have the x plus 2. All right. So how can we find the x plus 2 here? Well, here's the thing. Let's choose a delta here. So let's say we let delta be 1, for example. So let delta equal to 1. Then, if we have a look at the bound of this part over here, so we have that, well, x minus 2 is less than delta, or less than 1. The easiest one that you could work with is just 1, but as long as it's greater than 0, you could choose any delta to work with, but the easiest one would just be the 1 here. All right, so that means we could use a little bit of algebra here. Rewrite this as 1 less than x minus 2 less than 1. Okay. What we want here is the upper bound. We want an upper bound for x plus 2. So in order to get the x plus 2 here, we have to add 4 both to all sides of this inequality here. Why? Well, see that when I add 4 to all 3 sides here, then I would get 3 less than x plus 2. This is going to be less than 5. Aha. So now we have the upper bound for x plus 2, which is just going to be 5. So that means, so now what we have is that, well, so let's start from here. We have the x minus 2, x plus 2 is less than delta of x plus 2, but this is also less than 5 times delta because of the x plus 2 here. We now have an upper bound. So this is the x plus 2, and this is the x plus 2 here, or which is less than 5. So that comes from this part here. Okay, so what the thing with delta is that we could always choose more than one delta here. So there's a second delta that we could actually choose because the end goal here, we want to show that this is equal to epsilon, right? So once again, I'm going to say, well, let delta, in this case, if we want to have it as epsilon, we could just let this delta be equal to epsilon over 5. So that once we put this in, we have 5 times epsilon over 5. This is equal to epsilon. So therefore, we have shown that, well, x squared minus 4 is indeed less than epsilon. So which means that the limit as x approaches 2 of x squared is equal to 4. And the proof of this limit is done. So whenever you're dealing with something like this, whenever you have more than two bounds or more than two factors in a function, it's best to find the upper bound using delta is equal to 1. So the choice of delta that we actually chose here, so we let delta to be the minimum between 1 and epsilon over 5. So this is an important number that we choose. So we could choose a delta that is equal to 1. We could also choose a delta that is equal to epsilon over 5. So this is why we would have this as our delta here. So we could choose any one of this. And as a result, it would always give us less than epsilon. So it's like the first step, we choose 1 to get the upper bound for 5 for x plus 2. And then we use that, well, use the epsilon over 5 to get the epsilon at the end. All right. So let's have a look at some one-sided limits here. So there are two definitions. So for the first one, we're talking about the right-hand limit. So we say that if the limit as x approaches a from the right of f of x is L, then we say that for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus a is less than delta. So previously I did not include the delta because it should be obvious that it's going to be greater than 0. But this time, since there's no bound here, I don't, or since we're only working with one-sided, I don't need the absolute value. So that's why we have to make sure it's less than 0 this time. All right. So anyway, so if 0 is less than x minus a is less than delta, then that means the distance between f of x minus L is less than epsilon. And similarly for the limit for the left-hand limit, we instead of 0 less than x minus a is less than delta, we would have negative delta is less than x minus a is less than 0. So let's have a look at two examples here. So for the first one, we want to show that the limit as x approaches 0 from the right of x, the square root of x is equal to 0. So we do the same thing. So let me draw a diagram. So this is what the one-sided limit would look like. So this is our square root function. And we have the delta going to be from the right side, and from 0. So that's our delta there. And our limit we want to show is going to be 0. So that means if we have a range here, so if we let epsilon be closer to 0, we want to show that it's between this range over here. That's our goal. All right. So let's start with the definition of the limit. So let epsilon greater than 0 be arbitrary. And since the limit as x approaches 0 from the right of the square root of x is approaching 0, then we say that there exists a delta greater than 0 such that if, so the x minus 0, which is equal to just x, is less than delta, then the conclusion is that, well, if we have f of x minus L being the square root of x minus 0, which we could also just write the square root of x because that's always going to be positive. Okay. But here's the thing. Since x is less than delta, then that means the square root of x has to be less than the square root of delta as well. And so we can then write less than delta, the square root of delta. Now we just have to make a choice of delta here, since in the end we want epsilon, right? So how can we get rid of or in the end we want to show that it's equal to epsilon? So that means we have to choose delta to be epsilon squared. So choose delta to be epsilon squared. Why? Well, if we put the square root of x here, this is less than delta, but that is going to be epsilon squared, right? So that means the square root and the square now cancels out, so that we would just get epsilon in the end. So what that means here is that the square root of x minus 0 is less than epsilon, which also implies that the limit as x approaches 0 from the right of the square root of x is equal to 0 indeed. And that's the end of the proof for example 3. Okay, so the last example I will go over is the one-sided limit that's going to be on the right side, or the left side limit. So we have a similar problem. So we want to show that the limit as x approaches 2 from the left of the square root of 2 minus x is less than 0. So if we want to draw this visually, so we have 2 over here. This is the function. So 2 from the left, so we want to show from this side. So that means here's 2, 0. Let's say this is 2 minus delta. This is 2. Then we want to show it's equal to 0. So that means we have some epsilon positive, some negative epsilon down here. So epsilon, negative epsilon. So we want to show that it's in this specific region over here. All right, so we're going to start by saying, well, same stuff. Let epsilon be greater than 0 be arbitrary. Okay, so since the limit as x approaches 2 from the left of 2 minus x is equal to 0, then we say that there exists a delta such that if, so instead of delta from the right side, we're going to use the lower bound for it. So if, so minus delta is less than, so if negative delta is less than x minus 2, or also note that this could also be written as 2 minus x is less than delta, then, well, what we have here is that f of x minus L, which is going to be the positive square root of 2 minus x in minus 0. So the square root is always going to be positive, so I'm just going to use the positive version. Or I don't need the absolute brackets here. So now we have 2 minus x. Okay, so since 2 minus x is less than delta, so that also means that, well, the square root of 2 minus x is less than the square root of delta. So that means this is less than square root of delta. And the delta here should already be obvious because it's going to be the same one that we have chosen in the previous example. So we're going to choose delta to be epsilon squared. So then, so we have the 2 minus x, which is less than square root of delta, and that is going to be the square root of epsilon squared, which is just going to be equal to epsilon. So what that implies is that the square root of 2 minus x minus 0 is less than epsilon, which also implies that the limit as x approaches 2 from the left of square root 2 minus x is equal to 0. And the limit is proven. Okay, so that's going to be all for this exam, this topic here. I'm probably going to make a part 2 of the definition of the limit where I go ahead and explain the infinite limits. But if you have any questions about the concepts that we have talked about here, how to prove the definition, uh, how to prove the limit using the definition of the limit, you can just feel free to let me know in the comments down below. So I will see you guys in the next lesson.